Hello friends, welcome back to my channel. Today I would like to share with you the concept chemical energetics. Let's first look at the topic exothermic and endothermic reactions. Chemical reactions that transfer heat energy to the surroundings are described as exothermic. Therefore, the product contains less energy with respect to the reactants. In an exothermic reaction, the temperature of the surroundings increases. So here is an exothermic reaction. Magnesium plus H2SO4 gives MgSO4 plus H2. The energy is being released. Other examples of exothermic reactions include the combustion of fuels, the oxidation of carbohydrates in the bodies of animals and plants, which is called respiration, the reaction of water with quicklime. Quicklime is otherwise called calcium oxide. Chemical reactions that absorb heat energy from the surroundings are known as endothermic reactions. In an endothermic reaction, the temperature of the surroundings decreases. Therefore, the products contain more energy with respect to the reactants. Example, when sodium hydrogen carbonate reacts with an aqueous solution of citric acid in a test tube, the temperature of the reaction mixture in the tube decreases because the citric acid and sodium hydrogen carbonate are absorbing the heat energy from the solvent, the test tube, and the air. Other examples of endothermic reactions include the decomposition of limestone by heating. All thermal decomposition reactions are said to be endothermic. Photosynthesis, in which the energy is supplied by sunlight. Dissolving certain ammonium salts in water. Here is an example. NH4Cl plus water gives ammonium ions plus chloride ions. Enthalpy change. Enthalpy, denoted by H, is an indication of the total energy of a substance, and it cannot be measured directly. However, enthalpy change ΔH is measurable. Enthalpy change of a reaction ΔH is a heat change. Heat change can be heat absorption or heat evolution when a chemical reaction takes place. ΔH enthalpy change equals enthalpy of products minus enthalpy of reactants. In exothermic reactions, the enthalpy change is always negative. ΔH is less than 0. In endothermic reactions, the enthalpy change is always positive. ΔH is greater than 0. Here is an energy level diagram which shows the relative energies of the products and the reactants. The higher the energy, the higher its position. The first figure represents an exothermic reaction and the second one an endothermic reactions. Reaction pathway diagrams, enthalpy profile diagrams to show enthalpy changes. This is a reaction pathway diagram for the combustion of methane. CH4 plus 2O2 gives CO2 plus 2H2O. ΔH is given as minus 890.3 kilojoules per mole. The negative sign indicates that the reaction is exothermic. In an exothermic reaction, energy is released to the surroundings. So, the enthalpy of the reactants must be greater than the enthalpy of the products. We can see from the reaction pathway diagram for the combustion of methane, ΔH is negative. This figure represents the reaction pathway diagram of the decomposition of calcium carbonate. CaCO3 gives CaO plus CO2. ΔH is given as positive 572 kilojoules per mole. The positive sign shows that the reaction is endothermic. For an endothermic reaction, energy is absorbed from the surroundings by the substances in the reaction. So, the enthalpy of the products must be greater than the enthalpy of the reactants. We can see from the reaction pathway diagram for the thermal decomposition of calcium carbonate, ΔH is positive. Standard enthalpy changes. To make comparison of enthalpy changes a fair comparison, same conditions must be used. These are called the standard conditions. A pressure of 101 kilopascal, which is equal to 1.01 times 10 to the power 5 pascal, approximately 1 atmospheric pressure, a temperature of 298 Kelvin or 25 degrees Celsius. Each substance involved in the reaction is in its normal physical state, which can be solid, liquid, or gas, at 101 kPa and 298 Kelvin. Where solutions are involved, a concentration of 1 mole per dm cube is also involved. Standard enthalpy changes can be represented by the symbol ΔH, which is given here. This refers that the reaction is carried out under standard conditions. For example, methane plus oxygen gives carbon dioxide plus water. The standard enthalpy change equals minus 890.3 kilojoules per mole. There are various enthalpy changes which can be described according to the type of reactions. Example, standard enthalpy change of reaction, ΔHR, standard enthalpy change of formation, ΔHF, standard enthalpy change of combustion, ΔHC, standard enthalpy change of neutralisation, ΔHm, standard enthalpy change of atomization, ΔHAT, standard enthalpy change of solution, ΔHSOL, standard enthalpy change of hydration, ΔHHYD. Let's first look at the standard enthalpy change of reaction. It is enthalpy change when the amount of reactants shown in the stoichiometric equation react to give products under standard conditions. The reactants and products must be in their standard states. Enthalpy changes of reaction can be exothermic or endothermic. The equation that describes the reaction must be given. For example, H2 plus half O2 gives H2O. ΔHR standard equals minus 286 kilojoules per mole. Shows us the enthalpy change when 1 mole of water is formed from hydrogen and oxygen. In this case, 286 kilojoules of energy is released. However, if we write the equation as 2H2 plus O2 gives 2H2O, ΔHR becomes minus 572 kilojoules. 2 moles of water are formed from hydrogen and oxygen. In this case, 572 kilojoules of energy is being released. The next one is standard enthalpy change of formation, ΔHF. This is the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. The reactants and products must be in their standard states. Enthalpy changes of formation can be exothermic or endothermic. Examples: 2Fe plus 1.5 O2 gives Fe2O3. The standard enthalpy change of formation of any element in its standard state is 0. For example, carbon, which is shown as graphite, plus 2S gives CS2. Note that the state symbol for carbon is shown as graphite. This is because there are several forms of carbon, but the most stable state is graphite. We choose the most stable form when writing equations where enthalpy changes are shown. The next comes standard enthalpy change of combustion, ΔHc. This is the enthalpy change when 1 mole of a substance is burnt in excess oxygen under standard conditions. The reactants and products must be in their standard states. Enthalpy change of combustion are always exothermic. The substances combusted can either be elements or compounds. Example reactions are shown over here. Sulfur plus oxygen SO2. Methane plus oxygen gives carbon dioxide plus 2 water. The respective enthalpy of combustion values are also shown here. Standard enthalpy change of neutralisation, which is ΔH neutralisation standard. It is the enthalpy change when 1 mole of water is formed by the reaction of an acid with an alkali under standard conditions. The standard enthalpy change of neutralisation is always exothermic. This can also be thought of as enthalpy change when 1 mole of hydrogen ion reacts with 1 mole of hydroxide ions. Example is shown over here. HCl plus NaOH gives NaCl plus H2O. Neutralization enthalpy equals minus 57.1 kilojoules per mole. For any acid-alkali reaction, the ionic equation is H plus OH minus gives H2O. The other ions in solution, which are Cl minus and Na plus, are spectator ions and does not take part in this reaction. Standard enthalpy change of atomization. It is an enthalpy change when 1 mole of gaseous atoms is formed from its element under standard conditions. Equations are shown over here. Half H2 gives H, which is in the gaseous state. Sodium from solid is converted to sodium gas. Delta H atomization is equal to positive 107 kilojoules per mole. The standard enthalpy change of atomization of the noble gases is 0 because all of them exist as monoatomic gases at standard conditions. The standard enthalpy change of atomization is always endothermic, as energy is always required to break any bonds between the atoms in the element to break the element into its gaseous atoms. The next is standard enthalpy change of solution. It is enthalpy change when 1 mole of solute is dissolved in solvent to form an infinitely dilute solution under standard conditions. These are the given examples. NaCl plus aqueous gives aqueous NaCl solution. NaOH plus AQ gives NaOH AQ. An infinitely dilute solution is one which does not produce any further enthalpy change when more solvent is added. The standard enthalpy change of solution can be exothermic or endothermic. The next comes standard enthalpy change of hydration. It is an enthalpy change when 1 mole of gaseous ions dissolves in water to form hydrated ions of infinite dilution under standard conditions. As you can see here, Ca2 plus aqueous gives Ca2 plus aqueous. Delta H hydration equals minus 1650 kilojoules per mole. Water is a polar molecule. This means that it has a negative end and a positive end. The negative end of water molecule will be attracted to the cations, where the positive end of the water molecule will be attracted to the anions. The standard enthalpy change of hydration is always exothermic. How to measure enthalpy changes? We can measure the enthalpy change of some reactions by a technique called calorimetry. The apparatus used is called a calorimeter. A simple calorimeter can be a polystyrene drinking cup, a vacuum flask, or a metal can. As you can see here in this figure, represents a calorimeter. When carrying out experiments in calorimeters, we use known amounts of reactants and known volumes of liquids. We also measure the temperature change of the liquid in the calorimeter as the reaction occurs. The thermometer should be accurate to 0.1 or 0.2 degrees Celsius. Calorimetry relies on the fact that it takes 4.18 joules of energy to increase the temperature of 1 gram of water by 1 degree Celsius. The energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin is called the specific heat capacity, C, of the liquid. So the specific heat capacity of water is 4.18 joules per gram per degree Celsius. The energy transferred as heat is given by the relationship Q equals mc delta T, where Q is the heat transferred in joules, m is the mass of water in gram, C is the specific heat capacity in joules per gram per degree Celsius, delta T is the temperature change in degrees Celsius. Assumptions made in these calculations are the density of all aqueous solution is 1 gram per cm cube. Thus, numerically, 1 cm cube equals 1 gram. The solution has the same specific heat capacity as water, 4.18 joules per gram per degree Celsius. And delta H equals heat energy absorbed or released by number of moles of the limiting reagent, and its unit is kilojoules per mole. To then calculate any changes in enthalpy per mole of a reactant or product, the following relationship can be used. Delta H equals minus mc delta T. When there is a rise in temperature, the value for delta H becomes negative, suggesting that the reaction is exothermic, and when the temperature falls, the value of delta H becomes positive, suggesting that the reaction is endothermic. Also remember that the delta T is the same in degrees Celsius and in Kelvin. An example is shown here. A student added 50 centimeter cube of sodium hydroxide to 50 centimeter cube of hydrochloric acid. Both solutions were at 18 degrees Celsius to start with. When the solutions were mixed, a reaction occurred. The temperature rose to 33 degrees Celsius. How much energy is released in this reaction? So we use the equation Q equals mc delta T, 40 times 4.18 times 1.5, which is equivalent to 6,270 joules. Hess's law. Hess's law states that the total enthalpy change in a chemical reaction is independent of the route by which the chemical reaction takes place as long as the initial and final conditions are the same. We can illustrate Hess's law by drawing enthalpy cycles. These are often called energy cycles or Hess cycles. Example: the enthalpy change of a reaction from A to C is the same whether the reaction takes place in one stage, that is A to C, or two stages, A to B, then to C. By Hess law, delta H equals delta H1 plus delta H2. Hess's law is useful to calculate enthalpy changes that cannot be measured directly from experiments, theoretical reactions that will not occur under standard conditions. What are the steps to construct a Hess cycle? Write down the equation for the enthalpy change that you are asked to find and write delta H on top of the arrow. Use the information that you have been given to complete a cycle. Find the direct route and indirect route. The routes should not go against any arrows. Equations may be reversed when necessary, but do not forget to reverse the sign as well. Apply Hess law and form an equation to solve for delta H. The first one is enthalpy change of reaction from enthalpy changes of formation. We use enthalpy changes of formation of the reactants and products to calculate the enthalpy change of the reaction. Reactants gives products is delta HR. As you can see here in this picture, delta H2, which is a direct route, which is equal to delta H1 plus delta HR, which represents the indirect route. When we use Hess law, we see that delta HR equals delta H2 minus delta H1. To calculate the enthalpy change of the reaction, use this type of enthalpy cycle, we use the following procedure. Write the balanced equation at the top. Draw the cycle with elements at the bottom. Draw in all arrows, making sure they go in the correct directions. Apply Hess law, taking into account the number of moles of each reactant and product. An example is shown here. How to calculate standard enthalpy change of the following reaction. NaHCO3 gives Na2CO3 plus CO2 plus H2O. Given the values of formation of NaHCO3, Na2CO3, CO2 and H2O, these are the enthalpy of formation. The solution is shown over here. First step, apply Hess law. When you apply Hess law, delta H2 equals delta H1 plus delta HR. And Hess diagram is also shown here. You can go through it using the formation, enthalpy of formation values. Substitute that, insert the values of delta H, taking care to multiply by the correct number of moles, and rearranging the figures, you get delta HR standard equals plus 91.6 kilojoules per mole for the equation which is shown above. The next one is enthalpy change of formation from enthalpy changes of combustion. This is how the Hess diagram should be. Elements plus oxygen gives compound form plus oxygen, and those are the combustion products, which is at the bottom. Direct route is there, and indirect route is also shown there. So delta H formation equals delta H1 minus delta H2. To calculate the enthalpy change of formation using this type of cycle, write the equation for enthalpy change of formation at the top. Add oxygen on both sides of the equation to balance the combustion reactions. Draw the cycle with the combustion products at the bottom. Draw in all arrows, making sure they go in the correct directions. Apply Hess law taking into account the number of moles of each reactant and product. Calculate the standard enthalpy change of formation of ethane C2H6 given the relevant enthalpy changes of combustion are C plus O2 gives CO2, H2 plus half O2 gives H2O, C2H6 plus 3.5 O2 gives 2 CO2. All of the combustion values are shown here. And the solution is also shown here with the Hess diagram. While applying Hess's law, delta H1 equals delta HF plus delta H2. Insert the values of delta H taking care to multiply by the correct number of moles. And rearranging the figures, you will get the value of delta HF as minus 84.7 kilojoules per mole. Enthalpy of hydration from anhydrous salt. This is a Hess diagram representing enthalpy of hydration from anhydrous salt. Enthalpy and bond energies. During a reaction, enthalpy changes take place because bonds are being broken and formed. Energy in the form of heat is needed to overcome attractive forces between atoms. Bond breaking is therefore endothermic. Energy is released from the reaction to the surroundings in the form of heat when new bonds are formed. Therefore, bond forming is exothermic. If more energy is required to break bonds than energy is released when new bonds are formed, the reaction is endothermic. If more energy is released when new bonds are formed than energy is required to break bonds, then the reaction is exothermic. An energy level diagram showing bond breaking and bond forming for the combustion of methane is shown as A, and the B represents energy level diagram showing bond breaking and bond forming for the decomposition of hydrogen bromide, which is endothermic. Bond energy. The amount of energy needed to break a specific covalent bond is called the bond dissociation energy. We sometimes call this the exact bond energy or bond enthalpy. The symbol for bond energy is E. We put the type of bond broken in brackets after the symbol. So ECH refers to the bond energy of a mole of single bonds between carbon and hydrogen atoms. The bond energy for double and triple bonds refers to a mole of double or triple bonds. Two examples of equations relating to bond energies are shown here. Bromine giving 2 Br atoms. Bond energy of Br is positive 193 kilojoules per mole, and oxygen double bond oxygen gives 2 oxygen atoms. Bond energy is shown as positive 498 kilojoules per mole. The values of bond energies are always positive, endothermic, because they refer to bonds being broken. When new bonds are formed, the amount of energy released is the same as the amount of energy absorbed when the same type of bond is broken. So, for the formation of oxygen molecules from oxygen atoms, 2O giving O2, bond energy is minus 498 kilojoules per mole. Average bond energy. Bond energy is often affected by the presence of other atoms in the molecule. For example, the OH bond in water has a different bond energy value than the OH bond in ethanol. Even in the same molecule, for example CH4, the energy needed to break all the CH bonds are not identical. Therefore, bond energies are taken from the number of bonds of the same type from different environment and average out to get the average bond energy. The values are not always accurate. It is the average energy needed to break a specific covalent bond averaged from a variety of molecules in the gaseous state. The enthalpy cycle for calculating the average CH bond energy is shown in the figure below. Using the enthalpy cycle shown, the average CH bond energy can be found by dividing the value of delta H on the diagram by 4 because there are 4 CH bonds in a molecule of methane. The Hess diagram is shown here. Calculating enthalpy changes using bond energies. We can use bond energies to calculate the enthalpy change of a reaction that we cannot measure directly. For example, the reaction for the Haber process, N2 plus 3H2 giving 2NH3, the relevant bond energies are given here. Bond energy of N triple bond N equals 945 kilojoules per mole, EHH 436, ENH 391 kilojoules per mole. And the enthalpy cycle for the ammonia synthesis is shown over here with using the relevant bond energies. The calculations are shown over here, bonds broken, bonds formed, and the total is given as minus 93 kilojoules per mole. Thank you so much for watching this.